going to look a little different in some aspects. First off, something I don't normally have on a postulate sheet, I have a section to focus in on some of that vocabulary. So the diagrams that we talked about yesterday are on here for you to be able to label what does a chord look like, what does a secant look like, all of that wonderfulness. But one of the big things you're going to notice about this postulate sheet as compared to others is it's out of order compared to how we go through the notes, and that's a big thing, and there's a reason behind that, and we're going to talk about that. And on top of that, you're going to see a lot of equations popping out on this postulate sheet. This postulate sheet, the chapter 10, the challenge of this postulate sheet is knowing which of the theorems to use at any given time. So as you go through the problems, one of the key things you're going to have to look at is you're just going to have to say, okay, which picture does this look like? If I give you a picture that looks like that, which, on the front page, which postulate or theorem are you seeing?
Segment of chords.
Segments of chords theorem. The other piece about the organization of this unit, though, comes from the fact that if I flip it over, do you notice there's another picture that kind of looks like it?
Oh, that's annoying.
The difference is, on this postulate sheet, as best as I could, the front side focuses in on when you use segments. The back side focuses in on situations that you use angles. So if I give you a picture like this, it could be this theorem, or it could be this theorem. To know the difference is to know what's given to you on the picture. So let's say I get a little bit more specific with my picture.
That's angles.
Are those angles or are those segments? Those would be segments, which means you would want to use the segments of a chord. How can you tell something's an angle?
If the number's in the angle.
It'll be in the corner, and here's another thing it'll have.
Degrees.
A degree symbol. Angles will always have degree symbols. Arcs will always have degree symbols on their pictures. So, this postulate sheet is organized for you to be able to look at it and say, okay, I've got segments, so I need to look at this side, and this picture looks like this one.
What if it has segments and angles?
I'm not going to give you segments and angles. With maybe one exception. Yeah, but I'm not going to mess with you like that. Okay, I wanted to talk a little bit about that postulate sheet. I will tell you right now, when it comes to this chapter, filling in this postulate sheet is probably going to be more helpful than a lot of the chapters because of the fact that there's just going to be a lot of little formulas that are going to be very similar to one another. Now, we're not going to get to most of those yet today, but I did want to have that conversation with you before we got too far. Grab out your notes packet, open up to page 6, grab a calculator, and you might want a highlighter. That's a preferential thing on this section. There will be sections where you absolutely are going to want some different colored highlighters. So, today we're introducing our first true theorem. I introduced some key concepts to you yesterday that are gonna be things that we use throughout the chapter. But this is our actual first theorem. And it states that in a plane, a line is tangent to a circle if and only if the line is perpendicular to the radius of the circle at the endpoint on the circle. Okay. Essentially, and before we get into this, what does it mean if I say if and only if?
If and only if.
True.
I remember. Wait, hold on. I was just old.
It's been a minute.
Isn't it?
If and only if means one is true, the other one must be true. It doesn't matter which order you put them in. Something like x equals 5 if and only if 5 is equal to x. If that's true, that has to be true. If that's true, that has to be true. So, in a plane, a line is tangent to a circle. In this case, this is the line. Generally, we name lines by 2 capital letters if there are 2 points on the line, but there was one exception to that rule, and it's if it had a little lowercase letter by the arrow. So this time around it has that. Line M is tangent to circle. What's the name of this circle? Circle what? Circle Q. If and only if it is perpendicular to, in this case, QP. That's what the actual theorem says. The key thing that you need to know from this is tangents are perpendicular to radii. Specifically at the point of tangency. By the way, what does radii mean? Had some people confused when they saw it yesterday.
Radius.
It's the plural of radius. So, tangents are perpendicular to radii. Things being perpendicular means they intersect to create what? A right angle. So, if you see a tangent and a radius meeting on the edge of the circle, you should have a right angle. That's the key thing here. So, I see this circle here. Do you see some radii? I see one here. I see one here. Those are both radii. I wouldn't necessarily draw over them like I just did. I don't know why I did that. Okay, do you see a tangent? Or at least a part of a tangent line, technically.
Yeah.
Technically, it's a tangent segment because it stopped. It didn't go on forever. And is that tangent intersecting with the radius on the edge of the circle?
Yes.
Right here. That means this has to be a right angle. That's what that theorem gives us, that has to be a right angle. Now we're looking to solve for the radius. And it says, given that the point on the circle is the point of tangency, it's trying to tell you that, yes, that is a tangent. It's trying to tell you, yes, you can assume that that is a right angle. I want to solve for the radius. Knowing that that is a right angle, we now have a shape that we can work with popping up in our picture. Do you see a shape that we tend to use a lot? Maybe a right triangle? How are side lengths connected to one another in a right triangle?
By the right angle.
True, but what is the relationship between them? What theorem or formula could help us solve
A squared plus B squared equals C squared.
a squared plus b squared equals c squared? Knowing that that is a right triangle means we can use the Pythagorean theorem, a squared plus b squared equals c squared. The key thing that we need is what is the hypotenuse length? It is not 50. But you're looking at the right side.
R.
It's not r.
It's R plus 50.
That entire length across is the hypotenuse.
50R.
It's not 50r. Because what do I do with the 50 and the r?
You just do 50 times R squared, right?
Nope. If I want to find this length, what do I do with the 50 and the r? Add them. Is 50 plus r going to go together?
Yeah.
No, they are not like terms. That length is 50 plus r. Now I can do my Pythagorean theorem now. That's my hypotenuse. So that goes into the C part of Pythagorean theorem. I just have to be picky a little bit about how I plug it in. A and B are going to be these two sides. R squared plus 80 squared equals, when I do the 50 plus R, it has to be in parentheses before I square it. Once we get to this point of Pythagorean theorem, what do we typically do? We start doing the squares. The r squared stays r squared. The 80 squared becomes a big number. You got calculators. What's 80 squared? 6,400 indeed. Charlie, stay with us. Tom, you with us? Okay, so 80 squared is 6,400. To square a set of parentheses, you cannot simply square the individual pieces. To square a set of parentheses goes back to what it means to square something in the first place. What does it mean to square something? To times it by itself. To square, when you have a binomial, that's what it means when you got two terms, when you got plus or minus in between two things. It's binomial. To square a binomial, you must times it by itself.
Are we gonna do this page today too?
Yes. That page is a lot faster.
Looks scary.
How do I multiply this out?
Would you add the 50s?
Distribute.
It's just big distribution. This side's staying the same. R squared plus 6,400. For now. And you distribute. Everything in the one parenthesis gets multiplied by everything in the other parenthesis. I start with the 50 times the 50.
100.
No, times, not plus.
Oh.
2,500. That's what calculators are for. And then the 50 also has to be multiplied by the r, because everything in the first parenthesis has to multiply by everything in the second parenthesis. What is 50 times r? Positive 50r. Did the 50 of the first parenthesis multiply by everything in the second one already?
Actually, yes.
Yes. So now we move on to the next number in the first parenthesis, the r. It multiplies by this 50 now. It's another 50r. And now the r multiplies by the r. R squared. These equations get big and ugly before they get real nice. What do you think I should do next? Add the 50 r's. Combine your like terms. R squared plus 6,400 is equal to 2,500 plus 50r plus 50r is 100r plus r squared. Now this equation looks scary because it's got the squareds and it's got regular x's, but if I go to put like terms together, I want to put these r squareds together. They're on opposite sides of the equal sign. How do I move them together? Subtraction. Minus r squared minus r squared.
R.
They both die a painful death and they're gone.
Oh, okay. Oh. That makes it easy.
6,400 is equal to 2,500 plus 100r. That is a fairly easily solved equation. The beginning looks scary, but it gets down to something nice. How do I solve?
I think you subtract 2,500.
I think you are right. You get 3,900 equals 100r. Divide by 100. R will be 39. Again, they get big and ugly. But the r squareds will cancel out and it will become very doable.
Well, there goes all the space I have for my next problem.
It can become a problem here.
I think we can just shift it over.
Next problem. Same idea. A little bit less of me guiding you where to go. What is our goal to see in this picture? What shape?
Right triangle.
A right triangle. Where is the right angle at?
The right with the P start, or right with the P.
At P. Lily, which side does that make the hypotenuse? The one with the 24 on it, but is it just the 24? The 24 and the r, but when we put them together, do they actually add? No, they become 24 plus r or r plus 24, whichever way you want to write it. I'm just going to write it in the order that it is on the picture. So I'm going to do r plus 24. We connect side lengths of a right triangle using what theorem? And that's for anyone. Pythagorean theorem. Which side's the hypotenuse? Well, actually, I think Lily just answered that, didn't she?
Yeah.
So, Isabel, if I want to write out the Pythagorean theorem, how does it start? Yep, the a squared plus b squared equals c squared. What are you going to put in for a? You can make this the a. So r squared plus yep, that would be the b. Squared. Beautiful. Kylie, what comes next? We start squaring some things. R squared stays R squared. 36 squared.
1,296.
Ava, how do I square r plus 24?
Oh, you times it by itself and another pair of parentheses.
Times it by itself in another pair of parentheses. Because I left myself this big space here, I'm just going to do that here. Save myself a step. How do I multiply these? Distribution. Big distribution. How many things should I end up getting for terms? How many things are getting multiplied, in other words? Total of 4. Because it's r times r, which is r squared. Am I still multiplying this r, or am I moving on to the 24? R times 24. That's an easy one, 24r. Am I still working on the r, or am I moving on to the 24?
Moving on to the 24.
Move on to the 24. 24 times r.
24R.
Am I still working on the 24, or am I done? 24 times 24. 576. Sorry, I happen to know that one off the top of my head.
Me too.
Brody, once we get this far, what do you think I should do next? I can minus the r squared as I combine like terms. Gone, gone. 1296 equals, I'm going to combine these at the same time. 24r plus 24r is 48r plus 576. Do we know how to solve it from here?
Probably. Yes, we do.
I hope so. You should. It's algebra. Well, the rest of it was algebra too. It's linear algebra. Subtract 576. I wasn't positive if I had that right in my head. 720 is equal to 48r. Divide by 48, it's 15?
Yeah.
I trust y'all. I don't actually know the answer.
I do.
That's our radius. Guess what? The last problem on the page, you do the exact same thing. The key thing that people tend to forget is when you've got your right angle and you want to get your hypotenuse, what are you doing to get that?
50 plus R.
50 plus r, and do they combine?
No.
No. I just realized this problem's the exact same as one as the one above it. I actually put the same problem on here twice, which is fine. I wasn't going to do this problem anyway.
Yeah, I think, I did this all in my head. I'm really
Dang, skills. Okay, moving on. We got one more theorem. The next theorem's easier. This is one of the harder things that we do throughout this entire chapter, and I promise your phone's not going to help you with it, but it will go down to the office if it becomes a problem. The last theorem that we're talking about today works with this idea of there is such thing as a tangent segment. It literally just means a segment that is tangent to the circle, and typically what they do when they have a tangent segment is the end point of the tangent is the point of tangency. Now this theorem, way easier to work with. Way easier, because what this theorem states is that if you have tangent segments, two tangent segments coming off the same circle that have a common external point, in other words, they meet at the same exact place outside of the circle, then those two tangent segments have to be the same length, have to be congruent. RS has to be congruent to TS. That's what this theorem states. And congruent, a lot easier to work with than dealing with perpendicular and having to do our Pythagorean theorem. So, I see a circle. I see some tangents coming off of that circle. Do they share a same outside point? Yes. Therefore, these two things are congruent. What does congruent mean? Same, aka?
Equal.
I can set them equal. And I can solve. 3x plus 4 equals 28. I want to solve. What am I doing? 3x equals 24. Now I will divide by 3. X is 8. The problem says solve for the variable. We're done. If the problem said to find the length of one of the segments, you could plug it back in. Yeah, these ones are nicer. They get a little more challenging than that, but they still tend to be easier than what we did already. Okay. Problem B. Jocelyn, what should I do on this problem? Save for the fact that it's 12, not 2. Yes. At least that's what I heard. She said 12. I heard 2.
I meant 12.
Either way, you know what you're talking about. That's the key thing. You set them equal. I want to solve this. I can't call on people who aren't here. Dominic, if I want to solve this equation, where should I start? Get our x's together. Colin, what do I follow it up with?
You can add the 5 to 3.
4x is equal to 8. Divide by 4, x is 2. So, a little more challenging, but still linear algebra. Okay, again, we're going to step it up another little notch. Problem C. Are those tangent segments? They hit the circle out here at the same point, which means I can set them equal. x squared is equal to 9? Square root. When you introduce a square root, what should you also put with the problem? Plus and minus. Sometimes it has a need, sometimes it doesn't. Square root of x squared will be x. Square root of 9 is 3, and I've got my plus or minus in the front of it. When you've got the plus or minus, how many equations do you technically have right now? 2. One where x is a positive 3, one where x is a negative 3. You split it. The only thing you change is instead of writing plus or minus, you write one with positive, one with negative. Now the question is, do both apply? You can have negatives for variables provided when you plug them back in, you don't get negative angles or negative segments or negative arcs. If I plug a negative into a squared, does it stay negative?
I don't think
It can't, because when you square something, you're multiplying it by itself, and a negative times a negative is always
it can.
positive. Both answers are accurate answers. Can't forget your plus or minuses. We got one more problem and then we are done for the day. Trey, what's the equation going to look like for the last one? Yeah. Charlie. If I want to solve this equation, where am I going to start? Add the 22. Left with 4x squared. 78 and 22 together is 100.
Divide by 4 on both sides to get rid of that 4. So we need variable.
Yes. You need the variable squared to be alone before you could take the square root. X squared is equal to 25. To get rid of a squared, you take the square root. Not forgetting to put plus minus. X is equal to positive and negative. Square root of 25 is 5. So I get x is 5 and I get x is negative 5. Do they both work? Yes, because when I plug it back in here, that squared's going to make them positive. And it's going to work out. So, yes, the first theorem made things seem scary just because of the fact that generally the first one tends to be easier, but it's not always true in this chapter.
Up above that negative.
Nothing. It's the page number.
Oh.
Yeah, it's the page number there. Page 7. There we go. But